Hi, this is week 10. We'll wait for 5 minutes before everyone else joins. Let me start the session little early. So we were supposed to wait till 4 or 5. Seems like the viewers are occupied. I'll start the session. Um, Viewers who are viewing this lecture online over YouTube, please post a comment or you can mail me at vivek at the rate iisc.ac.in. So last week we had discussed about Bayes filter, where we calculated the state transition probability, and then we had a similar kind of a measurement probability as that of a state transition, and then we imposed a Markov property to simplify it further. And we also discussed about conditional probability. That's where everything started. And then for Bayes filter algorithm, there is something that we introduce a construct called belief. What we mean by belief is that that is what we take home, or that is what we take home from the algorithm to be true, regardless of what the actual thing is. This is what we take home. In order to get a true belief, what we do is in Bayes algorithm is a belief prediction. So let me just write it down. Bayes filter has something called prediction of belief, right? Prediction belief, right? So this is denoted by bell bar of xt. This is the state. So I'm going over a recap because what we will be discussing today, that is the Kalman filter and extended Kalman filter, are both dependent on what we are trying to do, what we did last week. This is a prediction, and then we do a measurement update, right? Measurement update. So this measurement update is nothing but our belief, right? So, yeah, prediction, we predict the belief. Yeah. So here, last week we did not make any assumption. Let's just point it out. We okay. Let me just write it in short. No assumptions were made. And why was this? Is that our state that we discuss xt is an enumeration between let's take head or tails, open or shut, and more than binary system. Let's have state 1, state 2, state 3. Yeah. So these were the kind of states we had, and these are discrete that you see. It's either head or tail. There is no measure of how close it is to head or how close it is to tail, and that is what maybe is required when we are dealing with probabilistic occurrence of anything. So like sensor data, we can have predicting of states. Maybe when your algorithm is complex or when your model is complex, we would require the position of a robot. So that is a numerical value, say x naught comma y naught, right? uh, let's take a robot is there, right? A robot is there. The position of it is x naught y naught, and this is in a domain, in a space, right? So because of this, we cannot have a probability state like head or tails. Mm, so you'll be having multiple x naught and y naughts. So you need to have a probability of how probable is that after a control signal ut, your robot is in x naught y naught. That is what we are interested in. And in order to have that, we need to make an assumption. The first assumption that we make directly leads us to a Gaussian filter. The first assumption is that our belief that we have is Gaussian. Now, what is Gaussian? What we mean that our belief is Gaussian is that let's take we have one point that is x naught y naught, right? And this is the true state. We have uncertainty surrounding it, right? Now, this true state is one point, like one accurate point, which we know is of probability 1. Probability of, let's take the state as S1 upon UT, okay, let's just omit UT. Probability that thing here is, this is the mean value. This will be the mean value of it, of the distribution. Actually, the total sum will be 1. This will be the mean value. Let's take mu naught, right? And okay, let's take one thing. Let's take this as a univariable problem, one dimensional problem, right? Or one dimension. So the point is clear. Then I'll move to multidimensional, right? So here I would say that there is only x naught rather than x naught comma y naught. There is only x naught, and this is my probability distribution. So let's take x naught is equal to 0. At 0, at 0 x, this is my x-axis, right? Positive, right? This is 0. Now the thing is that in negative of 0, my probability decreases. In positive of 0, positive side of 0, my probability also decreases. That means that the state has a mean at 0. This is the kind of construct we are making with Kalman filters or Gaussian filters in general. So the first assumption is that our belief is Gaussian. Yeah. And the second assumption that we make, right, in Kalman filters, let me just write it. We'll now introduce Kalman filter. Right? The second assumption is that, uh, which is that my motion model, like in base filter, here also we have our motion model, that is nothing but the probability of the new state given you have given a control signal, ut and x t minus 1, right? So this is nothing but our motion model. This model is also, is linear, rather it's not also, it's linear, right? So what we mean by linear is that the state xt is linearly depending on xt minus 1 and ut. So this is the assumption we make with Kalman filters, that our motion model is linear. So this is many people can recognize that. Okay, let me just put this later on the screen. Recognize this dynamics. Right? Is my mic on? Yeah. Okay. This is the linearized control of a system. So Kalman filters would directly work in those kind of systems. To account for the probabilistic nature of what we are dealing with, we add some stochasticity, that is ET, right? Epsilon T. So this is nothing but the normal distribution. Uh, when I say normal distribution, that means it's a Gaussian distribution. This normal distribution with a mean 0 and a variance, that is standard variance, the standard deviation square, right? Variance of RT. Now, so what it means is that if we go back to how a Gaussian distribution would look like, it would be 1 by 2 pi RT, the whole over root, times exponential of, yeah, if it's a univariable, it would be x minus mu divided by root over RT, right? If it is a univariable. For multivariable, I'll show the expression. So now we'll move on to the state transition probability. Like in base filter, here also we'll have a state transition probability. Right? Since this probability is a linear combination, yeah, a linear equation of the previous state and the control signal you have sent. So the probability of the state x t minus 1 will be nothing but the normal distribution around that state xt, right? So it will look something like this: at xt minus 1 plus bt ut, comma, here the stochasticity is put up as RT, because this particular expression is what we can invoke here. Instead of writing plus epsilon t, this epsilon t itself is a normal distribution. So we would say that the variance of this particular quantity will also be the same RT, right? So this will be in a multi variable Gaussian distribution. This would look something like this: root of 2 pi mod RT root of the entire expression, exponential e power minus half of this expression. Now we have to do something like x minus uh, mu, right? X minus the mean. Putting an error equation, let's take that xt is a measurement, or it's a known quantity that we know, and this is, yeah, xt is the known quantity that we know, and at xt minus 1 btut is what we predicted the state to be. This would be transpose, and this would be RT inverse. Now, since it is RT inverse, RT has to be positive definite, right? RT has to be greater than equal to 0, right? Or depth of RT, sorry. Depth of RT should be greater than equal to 0 times xt minus at xt minus 1 minus btut. Right? So this is our probability that we is a Gaussian distribution. Now we'll come to our measurement model. Here also we impose the same assumption that the measurement model is also linear, right? So in base filter we had probability of the measured quantity xt given zt given that xt has occurred. This was a known quantity because we knew how our sensor is. Either the sensor is biased towards a thing or it is unbiased. We would know what this probability is. Here we would take this as a distribution, again like a normal distribution. Zt, since we have told that this is linear, zt would be ct xt plus some stochasticity that is denoted by delta t. This delta t is again a normal distribution with mean as 0 and variance as qt, right? So now we get our probability zt given xt has occurred is nothing but normal distribution of ct xt comma qt. Right? You can substitute the same here. Instead of xt, there will be zt. Okay, let me just do it. 1 by 2 pi qt mod the whole over root exponential minus half times zt minus ct xt the whole transpose. Here you can see that there are multiple states. Because of those multiple states, it's a vector and we are taking transpose of that vector. And here it is qt inverse, and then here we would have zt minus ct xt. So this forms the two assumptions that we have taken, that our belief is Gaussian and our models, measurement and the motion model is Gaussian. The third assumption that we make is that our initial belief is also Gaussian, right? Here in base filter, what we did is that yeah, belief of x naught was say 0.5. For x naught, let's take head tail both were 0.5. If it was more than this, like let's take state 1 2 3, that will be equal to 0.3 recurring. Yeah, So we took something like a equal probability of occurrence, and then we started our initial belief with, right? So here we don't do that. Rather, we have it as a Gaussian distribution with some mean value. Belief of x naught is given as normal distribution. I'll not be writing the formula, rather I'll be denoting it by normal distribution with mu naught and some standard, some variance of sigma naught, right? This is again written in the similar fashion, multi variable Gaussian distribution. So these are the three assumptions that we make in Kalman filter, and based on this, I can have a good probabilistic method of saying of denoting a track or a trajectory that my robot has to follow. Right at every particular instance, I can say the probability, the belief that I'll have what is how close it is to the state, and based on that, I can uh, actuate my control signal so that it comes, to the closest one. Right. So that is how we are going to use these filters. Right. So let me just summarize a Kalman filter algorithm, right? So here we'll have a loop. So let's take the loop is for all states, x naught, right? Yeah, we'll have first, this is yeah, mu t is nothing but the state prediction or state measurement that we are doing. So here we were using xt, here we will be using mu t. So the mu t is the actual state. It is yeah no yeah mu t will be the actual state it is in, or the belief that we have that it is in that state, and mu bar is the prediction or the calculation or an estimate that we are making, that based on previous control signal and control input and the state, what is the new state, right? So that is nothing but the linear state that we have discussed. Okay, my mistake, I put x, it's mu t minus 1. So here there is no bar, please note, bt ut, right? From that we get to a belief prediction, right? So that is nothing but sigma of t is equal to at sigma t minus 1. Previous this is again an estimation, like this one was an estimation, like this one was an estimation, this is also an estimation, right? A t transpose plus the stochasticity or the variance, right? So I am assuming that everyone is aware of what a variance is. So let me just put a glimpse of it. Okay, let me just give you standard deviation as a measure. Let's take this as a mean. It need not be a straight line, it can be anything. So a standard deviance, or let's take variance, is a measure of how the scatter is, right? How the scatter is around your mean, right? So this will have, let's take, this is a standard, let's take, there is a measure of telling me this is how it is distributed, versus I have a mean something like this, and the scatter is really close, right? This has a low variance than this. So this is what the concept of variance is, and that is denoted by RT. Right? Now here we introduce the Kalman gain, that is given by sigma t estimated times CT transpose. CT is the measurement model. Uh, measurement model. CT times sigma T, again the estimation, CT transpose plus QT, inverse of this entire matrix. So this is the Kalman gain. You can go through the derivation that is given as a supplementary material in NPTEL. Even I'm not really sure. I've not gone through the derivation of how this gain is coming in. But here you can fairly get an idea of how things are being done. Now we come to the now we have done a state estimation. Now we will calculate our belief, that is what we know as true, or what we will take as true regardless of what the actual situation is. Mu t bar plus kt, the Kalman gain, zt, the measurement, that is the actual measurement, minus ct mu t bar, right? So this tells me like the error between measurements. Right? Let's take that I need to be at 0.5. I should be measuring 0.5. This is giving me 0.49. This is nothing but the error. That error is is multiplied with Kalman gain. Now, if the Kalman gain is high, such errors will be magnified, and that will be adding up to your state. If this error is low but Kalman gain is high, it's not going to be contributing in your state. And if the Kalman gain is low, regardless of your error, if you see how your Kalman gain is made, it is made out of your measurement model. If your measurement model, this product is low, uh, it only means that your estimate is low. Yeah, it means your sigma estimate is low, and because of that your Kalman gain comes uh, okay, if that leads to your Kalman gain reducing, and because of that you can see that this error is not going to affect much into your system, right? And now we need to get the belief. Since we have done a belief prediction, sigma bar, that will be nothing but I, that is identity matrix minus Kalman gain times the observation, or in controls we call it observation matrix. So this is CT times sigma T bar. Right? So this is with that we will end our loop. This we would do for all our states. Let's take we have in a continuous domain we have discretized it with 100 points. This loop is going to run 100 times at every time instant, right? So at every t, right? So this loop is going to run for 100 times at every t, so that we will get all our quantities calculated at that time for all those states. Okay? So here we can see one thing that let me just summarize. There I'll discuss what I wanted to say. We see that motion model is linear. We have problem with this model, and motion and measurement model is linear, right? Then initial belief is Gaussian, right? So these are the summary of Kalman filters, given that all our beliefs are Gaussian, that we have already told. So let me not iterate that here again. Here, measurement model being linear. Okay, measurement model being linear, we are okay with it. But the motion model being linear, we're not okay with this for one reason is that, let me take, I'm going in a curved trajectory. Right? When I'm going in a curved trajectory, I cannot linearize this. Right? If I'm doing a linearization, I am already adding some error into the system. And that, let's take something like a circle, right? With the center x naught, y naught. If I'm going to traverse over this, my locus, yeah. So let me just, okay, let me keep it x naught, y naught. X naught, y naught. This is x at time t, y at time t, right? If I take x t, y t, um, so that will be nothing but, let's take, this is r, okay, r cos omega t plus x naught, r sin omega t plus y naught, right? This is going to be my system. This cos and sine I cannot linearize. You may say that you can use Taylor series and linearize, but then it's not going to be, it will not do a fair job. And to complicate matters even further, we can go with an ellipse. This would be something like a cos theta, b sin theta, right? A and b are the major and minor axes, right? So, yeah. So we cannot linearize this system. So what we would do here is that we would have something called extended Kalman filter. Right? Here the measurement model also changes for one reason is that our xt, our state, is also changing. So it's better to have our measurement model which is also non-linear, right? So since here, even if we make it non-linear, a Kalman filter will not work until unless we have something linear. So how are we going to do this is that the state estimation, what we had taken, that xt will be equal to, let's take a t xt plus b ut. What happens, we generally write this control equation only near a pole, right? We linearize it near something and we get this expression only valid near that pole, right? So here what we do is that we will express xt as a function of ut and okay, I've made a mistake, t minus 1 here, ut and x t minus 1, the previous state, right? Then what I'm going to do is that I'm going to linearize this system. Now, when I say what is the difference between these two, is that I'm accounting for this point in this change. At every place, I'm linearizing this. Whereas the earlier system was only being linearized at a point that I knew. Right? So this, at every point, I'm linearizing it. So this function is being linearized using a Taylor series expansion. Right? And where am I going to linearize this expression? So I'll be linearizing this expression at its mean. So Taylor series expansion, right? So g of ut x t minus 1 will be written as g of ut mu naught or mu t, right? Here you can see t, this mean is changing, right? Plus g dash is nothing but a partial differentiation of this expression with respect to xt minus 1. Right, let me just write it down. Okay, I'll write it down in a moment. Yeah, give me a second. Yeah, so this would be nothing but ut at xt, sorry, g dash ut comma xt, right? This will be times xt, that is the um, state that I am at, xt minus 1, the state I am at. This will be, yeah, ut minus 1, sorry, mu t minus 1, mu t minus 1, xt minus 1, mu t minus 1. So this is going to be my linearized expression. Right? Let me just make it like this. Okay, it's approximately. This is a linearized expression of g ut xt minus 1. Now, since I was talking like when my pole changes, here this is nothing but this mu t minus 1. Right, so as time progresses, because of the control signal, I may have moved to a new location. Around that mean, I linearize my expression. So this accounts for that thing that there can be a non-linear dynamics, but the Kalman filter is still working because we are linearizing that non-linear, because by not because, by accounting where the position of the new state or the previous state is. Based on that location, we are linearizing at that point. So that is how we are getting away with using nonlinear expressions in Kalman filter. Right. Now coming to the measurement model, that will also be some function h times xt plus delta t. Right. Yeah. Give me a second. Let me check if the recording is working. Yeah, it is working. Okay, I have little slow internet, so please bear with me. Yeah. So this h of t again can be linearized. Um, h of xt can be again linearized using um, the same expression, h of mu t plus h dash of mu t times, right, xt minus mu t. Right? So this will be the linearized expression for the same. Right? Yeah, yeah, yeah. So now we will come to the algorithm. G dash of ut mu t minus 1. I'll denote this as g, capital G, at time t. Here, please note that this is at time t because um, ut is at time t, and this t minus 1 is the state, but this entire thing is computed at time t rather than t minus 1. Right? And similarly, we will have this h dash mu t as ht, capital H at t. Right? Now the extended Kalman filter, what we will do with the previous thing is that wherever AT is there, that will be replaced by the linearized. Here you can see the linearized quantity, that is nothing but GT. Right? The expression forms the same. Now we will have GT. Okay, let me multiply it inside GT x t minus 1. Right? Yeah, plus g ut mu t minus 1 minus mu t minus 1 times g dash ut mu t minus 1, right? Yeah, plus some stochasticity. Yeah, here you can see that this entire term, right, this entire term is dependent on ut, right? Let it be linear or non-linear, we are not bothered about it, because we don't use b of t in any of our calculation, at least um, not in our belief prediction or belief measurement. We have in a state measurement. There again, here how the state measurement would come to be is that it will be just g of, right? We know this function, so ut x, yeah, okay. Let me just change the symbol, mu t minus 1. Right? This will be a state, right? There is no bt. Yeah. Now, wherever there are AT, we will be replacing it with GT, because now you can see that GT is what is multiplying it linearly. Right? So we will have our extended, yeah, we'll have our belief prediction. That would be nothing but AT, sorry, GT, the belief of previous state, GT transpose, right? Plus there is stochasticity, so we'll have RT, right? And then we'll have our Kalman gain, that will also be the same. Okay. And here wherever we have CT, you can see that that is being replaced, like here ZT will be equal to H of UT plus H dash, that is capital H, let's write it as capital H T X T, right? This capital H T is nothing but how it was like CT back then, right? HT transpose times HT sigma prediction, belief prediction T HT transpose plus QT. Still we have, here you can see the delta stochasticity that we have is still here, the whole inverse. This will be our new gain, right? And then we have the state, that would be the yeah, the state ut plus the new Kalman gain, and set t minus, here you don't directly replace ht, rather this is nothing but h of, right? Because you know this function, this h that controls your measurement model, you know this function, so you directly substitute this value in it, right? Yeah, this will be mu bar, and then we come to our belief measurement, that is I minus Kalman gain times H T belief prediction. Yeah. So this is the difference between these two. In this week, also particle filter was covered. It is very similar to what we have discussed here. So instead of taking anything like a continuous distribution, what we do is that in that distribution we take certain instances, right? Near the mean we would take certain more number of instances, right? And use it as a particle to the existing filter that we have. Instead of calculating for all the quantizations that we had, we would rather focus on these particles rather than the whole, right? And that is what particle filter is. And most of your questions are in the properties of these filters rather than applying these filters. So once if you go through the NPTEL lecture, probably it would be much more clear. And if you have any doubts in what I have explained, yeah, let me just write this. This is uni variable. Right? If you have any doubt with what I have explained, please feel free to mail me. Right? Since there are no participants, so I think I'll not take any questions. You can always mail your questions to me. Right? I'll end the session here. Thank you. Let me stop the recording.